The Tesla coil was the first system that could wirelessly transmit electricity, developed in 1891. Tesla coils are used for everything from early radio antennas, telegraphy, shooting lightning bolts, sending electric currents through the body, and creating electron winds. A Tesla coil consists of two parts, a primary coil and secondary coil, each with its own capacitor, a part that stores electrical energy just like a battery. The two coils and capacitors are connected by a spark gap, a gap of air between two electrodes that generates a spark of electricity. Essentially, the Tesla coil is two open electric circuits connected to a spark gap. Faraday's law of induction describes how an electric current produces a magnetic field and how a changing magnetic field generates an electric current in a conductor. This was a groundbreaking discovery. Magnetic induction makes possible the electric motors, generators, and transformers that are the basis of modern technology. To understand Faraday's law, we must understand electricity. An electric field is created by forces between protons, positively charged particles, and electrons, negatively charged particles. A sufficient voltage, which is the potential difference in charge between 2 points in an electric field, produces a charge imbalance that can cause electrons to move through a conductor. This movement of charged particles is an electric current. To put this into perspective, current is like water and voltage is like a hill. A large voltage is a steep hill down which a stream of electrons will flow. A small voltage is like a near flat plane with almost no water flow. Understanding magnetic fields is also crucial to understanding Faraday's law of induction. Magnetic poles always come in pairs, north and south, and create magnetic fields. The magnetic flux through a given surface is proportional to the net number of field lines passing through the surface, which is the number passing through in one direction minus the number passing through in the other direction. A change in magnetic flux can be produced by changing the magnetic field strength, moving a magnet toward or away from the coil, moving the coil into or out of the magnetic field, or rotating the coil relative to the magnet. Now let's tie everything together. Another scientist, Ampere, tells us that the current flowing through a wire creates a magnetic field around it. We can coil this wire so that the magnetic fields from the individual turns add together in the center to create an even stronger magnetic field. The power of the Tesla coil lies in this process called electromagnetic induction. Faraday describes this in his law. A changing magnetic field creates an electric potential that compels current to flow. Conversely, flowing electric current generates a magnetic field. When electricity flows through a wound-up coil of wire, it generates a magnetic field that fills the area through the coil in a particular pattern. We can represent this mathematically. A voltage is induced across the wire proportional to the rate of change of a time-changing magnetic field. To demonstrate this law of induction, we built our very own mini Tesla coil. We used a primary and secondary coil, a resistor, a transistor, a battery, and a switch to create a very simple version of the Tesla coil. The current in the coil produces a magnetic field, which in turn induces a current that powers the light.